this example is an applied optimization problem. And the big picture on all applied optimization problems is that based on the information that we're given in the word problem, we need to come up with an objective function, a function that we are trying to maximize or minimize. So we're going to be looking for keywords like biggest or smallest or largest, or maximize or minimize, words like that to help clue us in on what the objective function needs to be. Now the problem here is sometimes the objective functions have more than one variable when you're setting up the equation. Maybe there's more than one dimension if you're looking at something geometrically, and you're going to need some extra piece of information to be able to eliminate one or more of the variables so that you can get your objective function in just one variable. That extra piece of information that we're given goes into what we're calling a constraint equation that gives us another relationship between all the variables or among all the variables that are shown in your objective function. But in the end, we need an objective function with one variable, and we need to know what the feasible domain is for that variable. We need to know what intervals the variable even makes sense on. So for instance, if we're talking geometrically about something that's, like a physical fence in this problem, we know that, for instance, negative values for distance aren't going to make sense. But then sometimes we can even be more specific than just something needing to be positive, for instance. Once we have a function in one variable, and we have the interval for which it's defined, this becomes then just an extreme values problem. We can optimize that function over the domain and find out what the maximum or minimum is and answer our question, of course. And so that's going to be kind of the process that we demonstrate through this very standard problem. This is a fence enclosure problem. So for this example, we have a farmer that wants to build a fenced enclosure on his farmland for his free-range ostriches. He wants a rectangular ostrich pen. So I'm going to go ahead and draw my rectangle here, a rectangular ostrich pen. And he wants for it to have, built with 1,000 feet of fencing. So that 1,000 feet of fencing is some fixed amount. So we have fencing is 1,000. The total fencing is going to be 1,000 feet. Okay, so built with 1,000 feet of fencing material to be divided into 3 equal sections by 2 interior fences that run parallel to a pair of exterior side fences. So that's just helping you be able to draw the picture. And so what they're saying is add 2 of these central fences in the middle of this pen to split the pen into 3 equal enclosures. And we see that those vertical lines that we put in there are parallel to the 2 sides. Okay, so this is the picture that we're looking at, and we definitely need some variables here. So the way that I see this is we have a horizontal dimension here, we can call it x, and we've got a vertical dimension here, we can call it y. Okay, so let's keep reading the problem. It says determine how to set up the pen so that the maximum possible area. So we've got that key word there, maximum. Maximum is telling us that our objective function is going to be an area function because we want to find the maximum possible area enclosed. And in the end, to finish this up, we want to actually find out what that area is. So not only do we need to know how to make it to get the maximum area, we want to know the maximum area. So that keyword maximum for the possible area is telling us that our objective function is an area function. So the entire area that we have is the area of this rectangle. And so the area of the rectangle then would be x times y. Okay, so we see there that our area function has not just one variable, but rather 2 variables. And so that's where the extra piece of information, in particular the amount of fencing that we have, is going to come into play with our constraint equation. So the constraint equation is going to use the amount of fencing. In some sense, it's like the perimeter, but we've got to also include those other 2 extra vertical bars in the inside part of the rectangular fencing. And so we know that the total amount of fencing is 1,000 feet. So that 1,000 feet, what we see is we've got the bottom here of our rectangle here. That whole bottom has length x, and so does the top. So each one of those has a length x. So if we include those two sides, we have 2x. But then each one of these verticals, we've got the two outside verticals, the far left vertical, the far right vertical. Each one of those is y. But then we also threw in an extra 2 verticals here. So we've got a total of 4 verticals, each one with length y. So we would have plus 4y. So we just added up all of the fencing pieces together and set it equal to the total fencing length that we had, linear length there. And so that extra piece of information is the other way that our variables x and y are related to each other. And so we're going to be using that constraint equation to help us eliminate one of the variables in the objective function. Now, on these sorts of applied optimization problems, sometimes one plug-in is easier than the other. And that just comes with some kind of experience as you're tackling these problems. But as I look at this particular example, I see that a is equal to x times y. So really we're just multiplying the two dimensions together. Neither one is inherently more complicated because they're both just to the first power. They're both multiplied. Now looking at the constraint equation, in some sense x and y are similarly easy to handle just because, again, each one is x and y, they're each just raised to the first power, and so we're not having to be able to solve for either one of those. We're not having to like take any square roots or anything like that. And so in some sense it doesn't really matter at this point whether you solve the constraint equation for x or y. But let me just show you in a couple of steps why I choose to solve it for x. So first of all, I see that the 1,000, the 2, and the 4 have a common factor of 2. So if I divided both sides by 2, I could just have 500 is equal to x plus 2y. And so now when I'm looking at that, x and y are again both raised just to the first power, but we see that we could avoid dealing with fractions if we solve it for x. If we solved for y, we would end up with a fraction in there because we would have to divide everything by 2. Both sides, and that x already has just coefficient 1 now, so dividing it by 2 would introduce a fraction. So what I'm going to do here is I'm going to solve that equation for x. X equals 500 minus 2y, and then what I'm going to do is I'm going to plug that into my objective function, and that gives me a is equal to, and in place of x I put 500 minus 2y, and then I multiply it by the y that's there. So I've substituted my constraint equation that was solved for x into x in the objective function, and I'm going to go ahead and multiply this out just so that I can, in the end, take the derivative more easily and not have to use a product rule. So here we have the setup now. We have the objective function in one variable and we use the constraint equation. And so let's just move to the next page there. There's our objective function in one variable, and I'm reminding you what the constraint equation is. And we need that, and really we need the constraint equation here too, because we haven't gotten an interval yet for this objective function. We have an objective function. It's a downward opening parabola, so in some sense we kind of know where we're going to have a peak. But just for completeness here, because on some of the other applied optimization word problems, we have higher ordered things or more complicated functions, and so I want to just demonstrate the entire process here. We have the objective function. Our next goal would be to be able to find an interval on which that's defined, or on which the variable y is defined. So for the interval assessment, remember our picture has a rectangle, and so for us to even have a pin at all, both x has to be greater than 0 and y has to be greater than 0. However, we know that x is this 500 minus 2y, so we know that 500 minus 2y has to be greater than 0, so we could say 500 has to be greater than positive 2y if we add 2y to both sides. Dividing both sides by 2 tell me that 500 divided by 2, oops, sorry, that's not an equal sign, it's a greater than sign, would be greater than the 2y divided by 2. So that would mean that y has to be less than the 500 over 2, which is the 250. So combining these two pieces of information, we have that y has to be bigger than 0 but less than 250. So our interval then is y is in the 0 to 250 interval. Okay, so now we have our objective function in the single variable y. We know that the interval for which we are optimizing over is the interval where y is between 0 and 250. And so at this point, we are ready to optimize. So this gets back into just those more abstract problems where you have a function and an interval. Now we need to find the global max is what we're looking for because we're trying to get the maximum area. So to optimize, first we need critical points. The function is continuous everywhere, so it's definitely continuous on the interval 0 to 250. And so critical points and what's happening as we approach the endpoints is all we have to assess. So the critical points, we need the derivative. So a prime then is going to be equal to 500 minus 4y when we take the derivative of our objective function. And to get the critical points, we need to figure out where is it equal to 0. So a prime equal to 0. We've got 500 minus 4y is equal to 0. So that'd be 4y is equal to 500. Divide both sides by 4, and you've got y equals 500 divided by 4, which would be 125. Okay, so that's our critical point. We don't have any places where the derivative is undefined because this derivative here is just a line, and so that is our single critical point. Now, notice that that critical point is in the interval 0 to 250, so it's very important that we notice that. That's part of why we need the interval in the first place. And we've got options to be able to figure out whether this is in fact the max or whether we would be approaching a max on either endpoint or whether we would have a solution or not. So as part of justifying your solution, you do need to justify that this is a max. And really, I think the second derivative test is the nicest way to do this. And I can say the second derivative test works because there is a single critical point in this interval. That's really a key observation here. There is a single critical point in this interval. So since the second derivative test, if we take the second derivative, we see that the second derivative is -4, because remember our first derivative was 500 minus 4y. So we take that derivative again, and we have a double prime is the -4. In particular, it's negative, which means A is concave down, and so we see a max. So we have a local max at the critical point. So we have a local max at the critical point, and since it's a local max at the critical point, the endpoints would have to be getting smaller, and we could justify that. We could plug in each one of these values into the original objective function and see what's happening, where we know that we're looking at the limits really when we're looking at the endpoints because the endpoints are not included. But since we have a single critical point in the interval, the tails are less. I'll say tails here in parentheses or in quotes, meaning what's happening as we're approaching the endpoints of the interval, the 0 and 250. The tails are less. So what we're really getting is a global max. Okay. So we need to be able to make sure we are answering our question. So the question asked us, how do we actually get the max? Like, how do we construct the pin? And what is the max area? So what we have decided is that y equals 125. We'll go ahead and put units with it there. This is measured in feet for distance because we've got our fence length was measured in feet. So each individual dimension length would be feet. So we have that y is equal to 125 feet, but then what would x be equal to? Well, we can go back to our constraint equation. We have x is equal to 500 minus 2 times y, and y we decided was 125. So what that's telling us then is we've got 500 minus the 2 times 125 would be 500 minus 250, which would then be 250. So 250 feet is what our x is going to be. And then we also need to actually know what the area is. So the max area is going to be equal to your x times y. So it's going to be your 250 times your 125. And that's going to be 31,250. And it's going to be feet squared because it's area. And so with that answer, we have completed the problem. We always should make sure we go back and we reread the problem, or at least the very end, to make sure that we don't work really hard, get our y equals 125 and stop. We need to fully answer the question. Y equals 125 gave us all the information we needed to also figure out what the other dimension, the x, was, as well as what the max area was based on plugging in the two values or the value for x and the value for y.